All right, good morning. How are you guys doing? Doing all right? Okay, today we're going to wrap up everything I wanted to say about Equilibria, do a couple more examples, and kind of get started a little bit in acid-base, but primarily playing in MATLAB a bit. So I didn't plan like an extensive session, so I considered emailing you all, say, hey, bring your laptop if you're interested, but it's not going to take a whole lot of time for that portion. So if you have it, you're welcome to plug it in, get it ready, whatever, and follow along. But it'll just be kind of a simple exercise giving you some demonstration of what I'm going to give you as part of the homework or part of the first steps for an assignment. So I need to figure that out and get myself organized. So my plan is to give you guys a first homework assignment during this week so that you can begin working on it. But I need to get there. Still need to organize my thoughts on that and assemble that. So, okay, so that's the plan for today. A bit more equilibrium, a few problems to kind of see how the pieces come together and shape some fundamental derivation of our equilibrium constants. Okay, last time we left off talking a little bit about chemical activity and pure elements, the difficulty in achieving high purity, things like that. So this was kind of what we were talking about, the example of pure gold or pure carbon in the form of diamond and things like that. All right, so that led us to this problem, which we didn't quite get to. So we'll start here. The problem, well, first of all, we're kind of building on this knowledge that some chemical potential, which we had described as a lot like potential energy in like a gravity, mass times gravity type of system, and maybe a ball at some elevation, is equal to, so the chemical potential for some species in a solution is equal to the chemical potential of that species at standard state plus RT, natural log of that activity. So basically some standard starting point plus RT is gas constant times the current temperature. That takes care of just the energy of the environment, so to speak, times that natural log of the activity of that species. Okay, so the question then says, looking at gold and chemical potential here, we have this reaction, the potential for, I think this is silver on a gold surface or interacting with gold, is equal to the standard state plus RT ln of the activity there. So it says if the activity of silver in in solid gold, namely the activity of gold subscript silver, or excuse me, the activity of silver, which is the subscript interacting with gold as the superscript here, is measured on the mole fraction scale. What is the value of RT natural log of silver at 25 Celsius when the activity is 10 to the minus 3, 10 to the minus 13, and 10 to the minus 23. And it gives us the value of R. That's part A, and part B says, since the standard is a finite number, how does this trend affirm what we've talked about for the value of chemical potential of silver dissolved in gold as it becomes very small? Okay, so take a moment to calculate that. right. So if we put those calculations in, should be as straightforward as using the values provided. Now we don't have, I don't think we're given a standard state, are we? No. So we can take a look at least at the right side of that equation, which is probably what they asked us to solve for, right? Yeah, what is the value of the RT ln of A? So calculating those, we can then consider that, okay, given some value for the standard state activity, that would, that gives us something to think about, which is part B. Okay, so each of these, we should get -17, -74, -131 kilojoules per mole for each piece. And it makes sense if we stop and think about when we put in the natural log of a very small number, the smaller that number gets, the larger and more negative the result is for that natural log. Because e to the what equals something very small, it has to be a large negative number. Okay, so hopefully that kind of makes some sense, so that that entire value of the right side of that equation gets smaller and smaller, or rather a larger negative number. So if we think about the part B, it says, well, what we talked about last time with the very small amount of some element being in a system, given some standard state, eventually the chemical energy here, or the chemical potential, is going to be negative as a whole. Even if this is, let's say, positive 100, we would see that, okay, at first it's still a positive potential, and then eventually we get to a point where it's negative and therefore going to drive that reaction, or rather be really difficult to pull it off of the gold. So it says the smaller the activity becomes, the smaller the overall activity will become, because that piece is constant. And smaller meaning, potentially more negative in that sense. Okay, so we could take a look at a variety of kind of typical chemical potentials, either gas or aqueous phase. And so a few examples here, we can see many listed here are negative chemical potentials at under 25 Celsius in 1 atmosphere. So, and these are the standard potentials, rather. So we can see one thing we'll notice here, we are defining the activity of H plus as 0 here. That's a kind of one kind of a definitional thing that we reference a lot of other things to, and we'll see that again in a few minutes. And so kind of in reference to that standard hydrogen potential, we can say other things have more or less potential energy. Okay, so let's take this to another example here. We want to find the Gibbs free energy, not just the standard potential energy, for a reaction. So the task is first to compute the value of Gibbs free energy at 25 Celsius, excuse me, that's the standard Gibbs free energy, at 25 Celsius for the reaction by which gaseous oxygen dissolved in water, namely oxygen goes to oxygen gas goes to oxygen aqueous. Now we're going to have to look up stuff, so I don't want us to feel like we have to get the exact numbers here. We'll rely on the textbook to do that, but write out what it would be the process to get there. And so you're kind of gearing your mind to say, okay, well, what do I need to accomplish that? All right, so I'll show you my thought process right now, and it actually was, I think, last time where I was. So it's been a few days since I've looked at this particular problem, so I'll kind of share with you my initial impression, and then we'll look through the answers together. I think that what I was recalling was, well, one thing we know is the standard potential is the Gibbs-free, at standard temperature and pressure, the Gibbs-free energy is the same thing as the Gibbs-free energy at standard state. That's one relationship we might could use, and it does tell us 25 Celsius. Another thing we could say is, well, at equilibrium, the delta G goes to 0, and then we end up with this relationship where that leaves the delta G naught equal to RT ln of the equilibrium constant. So I think treating these separate, and then as I'm thinking about it, we probably have more specific data from a lookup table to answer A, and then we'll use this relationship for part C, and kind of consider that for part B as well. So I think that's where the book's going to go with this. So let's take a look. Okay, so from a table, 2.2, which is probably what we were just looking at. Yep. So we could have come back to here and checked this table for this value. And probably with the water. So we could say delta G for formation, the standard, is 0 for oxygen gas. They're saying we know that, so that should just simply be that the delta G for formation at standard conditions, we were at standard conditions is 0. Perhaps that's something that I should have covered and as a special detail, but we'll just take that for granted for a moment. Then we can calculate the delta G naught equal to, see that 16.52, that should be this value here, yep. So that's, we could call it delta G naught for water, or for oxygen dissolving in water, right? That's what we see here, and our units are up here, right? Okay. And then minus the formation for gas, which we're reminded should be 0, and that gives us our answer there at 16.52. So that was a lookup table. Then if we think about, well, what units would be the K for this reaction, essentially we've got oxygen gas dissolving in oxygen, yielding oxygen that's dissolved, and you can add water to both sides if you want, but at the end of the day, it's going to be the products over reactants, right? So the K will be the product, so oxygen, the aqueous dissolved times water. Waters will end up canceling. And on the bottom we have oxygen gas, which is likely going to be a mole fraction, right? So that's good, should be on the top, the molal concentration of oxygen, so that's moles per kilogram or lowercase m, pretty much the same as moles per liter, which is kind of the shorthand I was using, divided by the mole fraction, or I suppose another way we could write that is the partial pressure, right? And that's why we're saying atmospheres here. So the portion of the atmosphere that is oxygen, and in this case it wasn't really specified, just gaseous oxygen, so we might have a container with pure oxygen and we're checking that, right? So then at 1 ATM surrounding and we're not pressurizing the system, we just have pure oxygen, that would be 1 ATM. But if we just had air, like in my thing here, that would be like 0.2 ATM, right, or thereabouts. Okay, so either way, one way or the other, we're accounting for how many moles of oxygen are in there. Okay, so then C says use the value to compute K. So essentially we can kind of take a look back at, here's our relationship. We know R and T, and natural log of K should then give us the delta G naught. Okay, and we derived this equation before, which is doing essentially just converting the natural log to a log. That's what the 2.303 is doing. Okay, so we can then get that value. K is 1.27 times 10 to the minus third moles per kilogram per atmosphere. All right, and then I think I've got part D on the next slide, but go ahead and take a look right now and let's try to answer this. So it says when the total air pressure is 1 atmosphere, the pressure of oxygen is 0.21 atmosphere, so it's basically just regular air. For what value, or for that value, what is the concentration of oxygen, aqueous, so dissolved oxygen, in molality and in milligrams of oxygen per liter? So should have everything you need to solve for this at this point. All right, so should be a matter of rearranging the equilibrium equation here. K, the waters cancel, so we can get the aqueous concentration by itself if we multiply, not divide. Sorry about that. It's not, didn't do that right. So it'd be 0.21 times that 1.27 times 10 to the minus 3. Of course, you could try to do it backwards like I just tried, and that's going to be the wrong answer. So it'd be K times essentially that gas concentration, so I probably shouldn't put it in brackets. So K was 1.27 times 10 to the minus third and 0.21 atmospheres for oxygen. And then, of course, once we get that value, that'll be moles per kilogram, and that's going to be the mole concentration we're asked for, but we'll need to convert that to milligrams per liter as well. So at that point, we could be really particular about it and do the lookup table for the density of water to get liters from the kilograms, and we could use the fact that oxygen is 16 grams per mole as the molecular weight, put all that together, and that should give us the answers here. So it's very typical for the dissolved oxygen values in relatively pure water to be between 8 and 10 milligrams per liter at saturation for kind of typical near room temperature values. If you get really hot water, it's going to be lower. And again, that you can now start thinking about that. Okay, that RT ln of K, that's where the temperature is making some impact. Likewise, if you get colder water, you can get values, and we could potentially calculate that, go all the way down to 1 Celsius or something. We're going to increase the amount of oxygen that dissolves in the water. So now you have all the tools to calculate exactly how much oxygen is going to dissolve in water at given temperatures, and so now you can know at what temperature is, let's say, a trout stream going to support trout. They want a lot of oxygen. They can't handle warm water in large part because they need more oxygen than that. Okay. Any questions? Does this make sense? Give you a moment. All right. So I want to talk a little bit about standard free energies of formation, in particular for ionic species. So we've talked a little bit about several species that are non-ionic, but it turns out almost everything in water except for water is going to be some ion. And that's one of the things about water, is it's so effective as a universal solvent in terms of allowing things to exist at an ionic state and dissociating things that, like sodium chloride, into ionic species. It's very effective at that compared to other liquids. Okay, so if we consider how to calculate standard formation of different ions, we typically are going to start with some non-ionic state and see, okay, well, what's the energy going to take from, for example, hydrogen gas to H+. And so we can take a look at the reaction where we have hydrogen gas and chlorine gas reacting and ultimately yielding for us H+ and Cl-. They did this as a half reaction, sort of, or like this is not a half reaction exactly, but they did eat the left side to 1/2. Of course, you could have 1 and then 2 on each side over here, but in this sense, they're just saying the hydrogen is converting from essentially the H2 non-charged state, the Cl2 non-charged state, into the ionic components. So if we want to know the standard Gibbs free energy for this reaction. We can measure that experimentally, and it turns out at, under standard conditions, that is negative 131.26 kilojoules. Now that's for the total reaction. Now we talked a few minutes ago, and we took a look at that. We took a look at the lookup table that the standard Gibbs free energy for hydrogen, or excuse me, was it Gibbs free energy, or was that the chemical standard potential? Yeah, chemical potential, which is the Gibbs free energy of formation. For aqueous hydrogen, we define as 0. So in part, what that's coming from is convenience when we want to do measurements like this. We want to know for a particular ionic species, we actually typically need two things happening. One to get a positive charge and one to get a negative charge, because we can't ever have an imbalance of charges, and we have to ultimately have it uphold the charge neutrality principle in water. So that means if we're adding hydrogen and converting it to H+, then we're also going to be adding something to get a minus. Or if we're adding something to minus, we're going to also have something that gives a plus. And anytime we do a reaction then and take a look at it, we will have two unknowns, and maybe we can measure the one known experimentally. Given that, it is very convenient to go ahead and designate hydrogen as 0 as kind of a default starting point. And so the book's describing here that for this formation is 0 for both gases, then we can say in total the Gibbs free energy, the standard Gibbs free energy for this reaction is that negative 131. Since we don't know how much of that's coming from the hydrogen, how much is coming from the chlorine, we just assign it all to the chlorine side of the reaction. So there's that assumption. We give H+ the honor of being set to 0, and we just call it a special little thing. And in part, it's almost like the H+ is the inverse of an electron in solution. So it's almost just like, it's so fundamental to so many reactions. So it gets a little special treatment. We use that, and then we can say, all right, well, the standard Gibbs free energy of formation for Cl- then is that value that we calculated. And it turns out that's quite convenient. So if we do set it like that and treat H+ as the special little ion, then we can go on and say, well, now that we know something about the Cl-, we can go and use that to understand other systems. And so then we can expand out the knowledge, and it turns out this is quite consistent, and we do this in many cases. So the discussion continues to say, well, Cl2 plus Fe solid will give us Fe2 plus and 2 Cl-. And so then we can measure the standard Gibbs free energy for that. If we get that experimentally to be this value, then we can assign, based on that prior experiment, setting the hydrogen to 0, we now know the chloride. And so we have that information. We measure this experimentally. Then we can know now the standard formation potential for Fe2+. So this is coming from the prior slide calculation. And we can now see that we can get all sorts of calculations and information because we made one assumption and essentially said, okay, this is just, we're going to call that standard for hydrogen. Okay, so then we can do that computation. So this is one other piece that chemists often use to derive and to find all these pieces. So if we even go take a look back at table 2.2, all of that, in some sense, is likely starting, or a lot of it starting from here, at least for the ionic species that we see here. And in fact, it gives examples for both of these. Okay, for the non-ionic species, I think it's a little simpler. We can just measure and calculate. We don't have two unknowns. But for the ionic species, we have to take a little more care. Okay, one other thing we can take a look at is combining equilibrium equations. So we might need this at some point. And it's typically what we would look to do if we have a sequence of reactions, but we really only care about the sum, like the, let's see, the net reaction, right? So for example, the formation of iron hydroxides, Fe and OH, we might take Fe3 plus, OH minus. That'll give us FeOH2 plus, but that doesn't stay there very long because it's going to react with more OH minus. So that's just one step along the way. We can find the K value for that, but then we next have another reaction very similar to get FeOH2 plus. Perhaps we even would take it all the way to FeOH3. And that's, I think, likely to be precipitating as a solid. But let's just take these two for the moment. And we can take a look that if we look at it algebraically, we can add the reactions together in terms of adding the reactants with the reactants and the products with the products. So we end up with everything on the left. So we have Fe3 plus 2 OH minus. We added 2 of them here. So that gives us the 2 there, plus the FeOH2 plus. It's kind of the intermediate component, equals the stuff on the right, which is FeOH2 plus, and FeOH2 plus. So what we notice is the intermediate compound will cancel out of the equation if we look at it that way. But before we really go that far and cancel and simplify, we can also take a look at what, by definition, how the equilibrium constants combine. Because each time we make an equilibrium constant for one of these equations, what we're doing is we're saying it's the product of the products divided by the product of the reactants, right? So it's always kind of the products times each other to the appropriate exponents over reactants. Right? So if we then add more products, then essentially what we're doing is having, so this would be the products for reaction 1 and reactants for reaction 1. Then in essence, when we take the entire set together, what we've done is now said products from the first one times the products of the second. So because of the way we calculate the equilibrium constants, we're multiplying the K's together if we've added them. Does that make sense? Okay, so that's why it ends up making sense to say K is then K1 times K2, and we can simply multiply these two numbers together to get a new K for the entire 2 steps. We will also see that the pieces will cancel out in here a bit when we go to write that expression. So ultimately the expression would be Fe3 plus 2 OH minus goes to FeOH2 plus. So all that, you've probably looked at this before or seen stuff like this. Just wanted to make sure it's clear we're able to combine them that way. And in fact, we can also subtract one from another as well, but that does something that's slightly different to our equilibrium constant. Essentially, we're dividing instead. We can see that come out algebraically as well. So let's take a look and say, Well, maybe we take that equation we just used, Fe3 plus 2OH minus is in equilibrium with FeOH2 plus. And we could subtract from that a reaction where we have 2H plus 2OH minus yields 2 waters, right? So we can consider subtracting the water equilibrium equation. And so what we'll, essentially what we're doing is we're saying, well, to get that OH minus, we need to be consuming some water. We're dissociating some water. So that's effectively what this expression is kind of saying, like, all right, this is what's happening also. So if we subtract that, we'll get the total reaction is and the reason we're subtracting it, it would be kind of like flipping it and adding it, I think would be the same thing. So we're going to say Fe3 plus 2 waters, and we will get there, let's see. Well, let me read it out first and then we'll sort through this. Fe3 plus 2 waters is in equilibrium with FeOH2 plus and 2 hydrogens. So by subtracting, we are, I guess we could look at it this way, right? We could have looked at it as, and I'm just going to write freehand away from what this is doing. So we could look at it as Fe3 plus 2OH minus 2H plus minus 2OH minus is in equilibrium with the FeOH2 plus minus 2H2O. So what they've done is they've swapped things around, right? So the 2OH minus the 2OH minus, those will cancel, and we'll be left with the expression they provided, right? If we move the 2H plus to the right and move the 2H2O to the left. Okay, so that's how we get there. And ultimately what's going to happen with our rate constants then, what we had at first was, let's say the products here being FeOH2 plus divided by the let's get rid of that. Okay. Divided by the Fe3 plus here. Times the OH minus squared. So this would be the equilibrium relationship for the first one. And for the second one that we are subtracting would be the H2O and OH minus. Okay, so once we've added them together, we can write them all out again, and this would be the products of the final one. And what we should find is that if we were to take this one divided by this one, we'll get our answer here. Okay, so Okay, so we do see the H2O squared on the bottom. Essentially, that's what we get if we take this guy divided by this one, right? And we'll see that all arranges. So if we're subtracting, we can write it up that way and ultimately combine our equilibrium equations like this. Make sense? All right. Okay, so that's one piece I wanted to take a look at. So let's go through a quick example for that. Make sure that's making sense both conceptually and practically here. So let's consider reactions 1 through 3. The K values at 25 Celsius and 1 atm. And what we want is the K value for the overall reaction of those three together, yielding number 4. So we've got CO2 gas dissolving in water. That's giving us carbonic acid, H2CO3. That's in equilibrium with bicarbonate. And we also have water to consider as well. So give that a couple minutes and see what you think. All right, so I think if I take a look at these reactions, we're going to need to add the first two together because we need to get to HCO3 minus on the right. And if we add those together, these two will cancel, which will be helpful. And then we also need to get rid of water and end up with an OH minus. So I believe if we subtract the third one from that equation, that should get rid of the H2O from the left side of contribution there and ultimately leave us with a minus OH minus on the right, and that will come over here to the left, and the H plus will then cancel. So if we do 1 plus 2 minus 3, I believe that should give us the answer, which means all we need to do with the k's is say k total is the 1 times 2 divided by 3, right? And I went ahead and labeled those because they didn't. Okay, adding reaction 1 with 2, subtracting 3, doing so, yeah. And the answer then should be 1.5 times 10 to the 6 power. All right, make sense? Okay, last little thing I want to talk about is when we're setting out to find an activity coefficient, there are several equations we can do so. Ionic strength tends to be one of the most important parameters for determining what is the actual activity of some species. Now we can do some empirical calculations and experiments to study the effective ionic strength of something, but really we tend to make an estimate according to one of several theoretical derivations we see here. You've probably seen these before: Debye-Huckel, however you say that, the Davies equation, extended Debye-Huckel. There are several things, and some of them are more appropriate for different ranges of ionic strength. So just as a quick refresher reminder, ionic strength can be calculated as 1/2 of the sum of whatever ionic species are in solution times their concentration times the concentration times its charge squared. So if we had sodium chloride, for example, dissolved into water, then the ionic strength is going to look like 1/2. Well, let's do something slightly more interesting. Let's do magnesium chloride, MgCl2. So this is going to give us an equation that looks kind of like this. We calculate the concentration. This is the mole concentration, but like we often say, in a typical aqueous condition, we can kind of write that as molar. It would be magnesium 2 plus times that plus 2 charge squared. The square is going to turn any negative ones positive, so that's quite helpful. Plus the amount of chloride. Now we have 2 chlorides for every 1, right? So this is going to be Mg2 plus 2 Cl minus. That 2 is just calculated in the overall concentration. We don't include that as an exponent anywhere in here or anything like that. So it's going to be Cl minus times that -1 charge squared. So that's kind of the approach. That's what this little equation is saying. It's 1/2 times each concentration times its particular charge squared. So that's ionic strength, and that can be put into all sorts of different equations to find an activity coefficient. So if we need to do that, we can take a look. The Debye-Huckel equation is log of the activity of some species is equal to -A times that species charge squared times the square root of the ionic strength. And depends on temperature, but typically under standard conditions, A is this guy. Or I guess that has the temperature in it. And we can find all the other notes about parameters within these equations. We can see that this equation is valid for ionic strengths less than 10 to the minus 2.3. We can do the extended one, which gets us valid anywhere under ionic strength of 10 to the minus 1. And then the Guntelberg has a similar range, different approach a little bit. And then we can go a little higher with the Davies equation. So that's all to say, here are some different ways to calculate it. You've probably seen these before. We could take a look at them. I'm not asking you to memorize these necessarily, but hopefully to be familiar enough to say, oh, okay, there's a way to do that. Maybe on a homework assignment, you can go back and say, oh, there's a table, let me go find that. Here's this equation, and let's go from there. Okay. So with that, I think we're ready for to leave the ionic strength stuff behind us, or excuse me, the equilibrium behind us in terms of the fundamentals, and then start with acid-base chemistry. And I'd like to do that by starting with a little MATLAB, tiny MATLAB project. So I'm going to have you, if you have a computer, feel free to use it, or just use some paper and write out what you're thinking about how to do this. We can make a very simple script. I had to remind myself yesterday, spent some time doing this. I still haven't watched the videos I assigned to you, so I don't know exactly what you know from that, but I have a couple questions for you. The target, what I'd like us to do is, and I will do with you here in a moment, is to make a script that calculates and plots H plus and OH minus concentrations versus pH. Okay, so then what we're dealing with is the equilibrium constant for water is 10 to the minus 14th. We should know that. And of course, that's for water dissociation, like that. And of course, you also know that pH, that's really just saying negative log of H. So as we plot this, it's quite simple. We can just say, oh, well, pH 7 is 10 to the minus 7 for the H value, right? So we just need to make a plot that is, looks something like this, where we have pH on the x-axis and the concentration on the y-axis. And the H plus, of course, will be highly concentrated at low pHs, and it'll look kind of logarithmic. And the OH minus will do kind of the opposite. So it should look something like that. I didn't draw very well, but you get the idea, right? And then I'm also asking us to do this on a log plot. So I put a couple tips here, and I have a couple questions for you. So you did make some sort of figure in the practice, right? It was just one figure, or did you? Made a lot of figures. Okay, did you make multiple on one panel? Multiple lines on one graph, multiple graphs on one figure? Okay, there's a way to do that, and I had to remind myself yesterday, so we'll go through that. That's subplot. Okay, and then there's also a semi-log y function that we can use to tell it to do a log plot. Did you guys use for loops at all? Introduced to that at all? No? Okay, so I'll find, I'm confident that they have some introduction on using the if and for loop stuff. So I will show you today. I don't think you have to have it, actually. There's no reason you have to. But we'll do that. Briefly show you, and I'll find you some homework to refresh your memory on that. Okay, so I'm going to stop talking for 5 to 10 minutes. Then I'll start working on assembling the code myself, and you can just kind of watch what I'm doing. So you'll have time, 5 minutes, to think about it yourself, sketch it out, and then from there, I'll kind of explain my thoughts. And if I run out of time, I'll just pull up what I wrote yesterday and show you that. Okay, so have at it. Be right back. How's it going so far? Not going? What's that? We just entered KW was 10 to okay. Good. That's no problem. One other thing I'm going to write up here real quick is that we probably also want to have a substitution, so we know that, I'll just write it, so KW equals H plus times OH minus. So we'll use this at some point when, H plus we can find very easily by this guy, but OH minus then we can find by saying that's KW divided by whatever H plus is at that pH. Okay. All right. Set this out of the way. You guys have made a script, right? Done that part? Okay. So I'm going to So one thing you can do, I don't know if you knew this, but if you want to comment something, Control R on a PC does that. I think there's a way to undo that too. Just adds it. I forgot the hotkey to remove it, but or you just put the that. So I just write a little note about what I'm doing. The first thing we really ought to do is make sure we're in the right directory. So I'm going to go ahead and pull up right place. Just going to go to yeah, we'll do that. Okay, it's going to do MATLAB here. So we select a folder where the script is going to save, and then I'm going to go ahead and save it. And I just want to make sure I'm in that script. So I'll say H2O dis for dissociation. Then we're ready to go. Okay, so you've already got KW equals 10 to the minus 14. I'm going to go ahead and put a semicolon there to stop it from doing anything else. I'm also going to define a pH range that I want to work in. So I'm going to say pH. I'm just going to label it, right? So just making some variable name. And I'm going to take this from 0 to 14. But I kind of want to do a slightly more fancy than that because I want to do, instead of 0, 1, 2, 3, 4, 5, I want to take smaller time points. So did you do like arrays, like a range like this, 0 to 14? Okay, so the fancier way to do that is add in another semicolon or another colon and say, let's say 0.1. So then it's going to step that through by 0.1. So if I just save this and go to my command prompt and run that script, that's H2O dis, then it's going to just read out a bunch of steps right there for that pH range. It's going to say pH range equals 0, 0.1, 0.2, and so on. And it's not a bad idea to check what your script is giving you out as you go through it. I'm going to go ahead and put the semicolon so I don't see that every time. And then I'm about ready to make some calculation. Now what we want to do is calculate, the next step is to calculate values for H plus at every pH. Now it's kind of obvious pH is negative log of H, so we could take H is equal to the, we'll say H plus is equal to 10 to the minus pH, right? So we can do that. How we do that, we could probably just simply do some sort of a array multiplication and get our answer. I don't like to do that because I'm just linear algebra stuff and using matrix, like multiplying matrices and things like that. It's just not so intuitive for me, so I'm going to use a for loop. So the way these work is you write for, and it's like, ooh, something's going to happen. And then you give it some, it's a lot like summing something where we say, or integrating something from 0 to something, right? It's going to take one by one, stepwise. It'll say, like, we could say from 0 to 100. And then it will go in, I'm sorry, I'm going to give it some descriptor. So from I equals, and then it's going to take I starting at 1, and then 2, and 3, or well, starting at 0 actually. It will then count those through. So what I'm going to do is I'm going to say, I want this to encompass my entire pH range from 0 to 14, but by each step. So there's actually going to be more than one step. There's going to be 10 steps for every one integer, because I have to count the 0.1, the 0.2, the 0.3. Each of those I need a calculation. So I'm going to do 140 calculations, or however big this pH range is, 1 by 141. So I'm going to say from I equals 1 to, should it be 1? Yeah, to the length, that's a command we can use, of pH range as it already thinks I might want. So for the entire length of that, the length is meaning how long is this array, and it's 141 long because it was 14 times 10 basically. So from 1 to the end of it, I'm going to take different steps. And what I'm going to calculate in there is I'm going to calculate a value for, I'm going to call it H-conc, for H concentration. And I'm going to make this an array also. So this is like taking an Excel spreadsheet and saying, I'm going to make 141 rows. I have my pH concentrations as an X value range that I'm going to plot. That's pH range here, and it's stepping by 0.1 every time. And then the next row I'm calculating is this H concentration, and I'm going to calculate that based on what's in the pH times something else. So I'm going to say, when I use the brackets here, I can say I for the, that's counting down the Excel rows, basically. So I is 1, that's row 1. Once this for loop completes, it'll go to the next one and say, okay, now I is 2, and we're going to calculate on that second row. So that's what the for loop is doing for us. It's going to say, from starting at that first value until we get to the last value, we're going to do this calculation. And I can call back to that I every time to say, we're going to calculate this one, and then we're going to calculate this one, and I is going to increase once every time. That's the for loop. Okay, so I'm going to say the H concentration is that, so at that first cell, and I think that's all I have to do here, and set that equal to, here's where I do the calculation, right? So H plus is equal to 10 to the minus pH. So I can say 10 to the minus, and here I'm going to call back to pH range at I. Okay. So let me just go ahead and check to make sure this is working properly. The last thing I need to do in a for loop is to end it, and so I type end. Kind of simple that way. So I'm going to save this and then run it again. Didn't get an error. That's good. I do have some alert. Okay, so maybe I did something a little wrong. But if we take a look here, it should have calculated it. Now I should have a value of H concentration. And sure enough, they're pretty small at the high pHs. And let's see. They shouldn't really be low here, so that's a little strange to me. Or maybe I'm misunderstanding. All right. Well, let's just assume for a moment that's good, or maybe I should have started at 0. I think that's going to break it. No? Okay. Let me just take a look what this alert is telling me. Okay. I think that's fine. I don't think we need to worry about that. All right, so that presumably gives us a concentration for H. We also need for OH. So now we can add that here. I'm going to say OH_conc for that. I equals, and I think what MATLAB was worried about is my hconc variable is growing every time I iterate the loop. So maybe I should define it up in front and say, just put it as zeros to start with, but it doesn't matter, I don't think, in this case. So I'm going to do the same thing, but here I'm going to say, well, now we have to go back to our calculation and substitution to say the OH concentration is going to be the Kw divided by the H plus, right? So here we can simply say this is equal to Kw divided by, we can actually just simply use the H const that we just calculated at I. So we calculate the H plus and then we calculate the OH minus based on that. And then we get to plotting. Assuming that's working so far, let's just do a quick check. Oops. Did something wrong. Oh. What did I do? All right. Let's, for a moment, for the sake of brevity, we're going to kill that and say plot, do subplot. Subplot, we're going to do, the first one is typically your, I think, X, so that would be pH range, then your Y, H concentration. Oh, I'm sorry, that's the wrong thing. Subplot is how many rows versus, so I'll do 2 rows, 1 column, this one will be number 1, and then plot the Y, let's see. I'm going to plot, I think it's X first, so pH range, comma Y, H conc, and I can even give it a little symbol. Okay, so I think I still did something wrong. I'm sorry. Oh, it's this. Duh. Okay, so it plotted and it pulled up over here. Okay, so I got a plot. And I made them look like little zeros. That's just a fancy little thing you can do. And I think this was not a problem here. It was just a problem with me going from 0, which was silly. And so now I can also say plot pH range, OH conc, and put some other symbol. I think that should work. Okay, so it overwrote it, so I think I need to hold the thing. And I know we're out of time, so I'm gonna stop in just a second. There's a thing we can say hold on, and then that will plot that one as well. Oh. There we go. Okay, so I think I didn't do everything quite right here, but I will give you some homework along those lines, give you some homework along for loop lines, and probably revisit this a little bit with a better polished script. But was this helpful? Does this make some sense? Would it be better if I had just showed you something already finished? Or do you like the watching me fumble? Okay, so kind of helpful, but maybe better if I didn't fumble. Let me know what you think as we go.